Is it visible?
Yes, it's visible. Yes.
So, good evening, everyone. So now I will uh, I will represent the real time. I will present the real time integration of solar and wind PMSG coupled with DC motor wind energy storage system for a standalone microgrid. So myself Riju Nandi, under the supervision of Dr. Arnab Ghosh sir and Dr. Krishna Raj sir. I'm doing PhD in NIT Rourkela. So this is the content. So first content in the introduction. Then I will go further for block diagram of the DC microgrid, take experimental setup, then conclusion references. Because it is experimental laboratory session, that's why we must go to the experimental setup. So introduction. Why do we need the intricate multiple renewable sources? First is resources diversification. Is combining different renewable sources reduces the dependence on a single source. Suppose you are using now only PV panel, so you only depend on PV panel. If you are using multiple sources like wind, biomass, suppose hydro, that time it depend on all the renewable sources. So it is about spreading out your resources so that you are not affected badly if one source fails. Suppose one source fails, suppose PV panels fails, then others renewable sources is going on. So second is grid stability. So uh, you have to keep your voltage in DC bus voltage keep constant. Also power you have to balance also power flow even when the generation on the load condition change. Suppose your generation change but when a load condition when change on decrease increase, that time also you have to keep the DC voltage constant, means DC bus voltage constant, also power flow balance power flow balance. So third part is reliability and resilience. So mixed renewable energy sources can withstand fluctuation and outages better, making the system more reliable to extreme weather condition and other disturbances. Last part is environmental benefits. So minimize environmental impact and support emission reduction goals. So minimum carbon gas is there. So there is no carbon also. So this is the environmental free. So third is application. So this is application remote village, suppose a remote area and islanded power system, a remote village or remote area system. So there is data centers and telecom system also, military and aerospace system, there's EV charging station, smart homes and buildings. So you can see that I have used that for the this is a PMSG. After the rectification, the buck converter is there. Then is a DC bus is there. So so for the PV panel, I have used the SEPIC converter. Then after that, output of the SEPIC converter goes to the DC bus. So also in parallel also there is a bidirectional buck boost is there for, and the battery is there for the charging and the discharging purpose. And this is the load. So that this is these two are the source, and this is the storage system. Okay. So when this two was not working, that time is to that time batteries discharge the voltage to the load, power to the load. Okay. So this you can see that the PV module and wind means this is a PMSG coupled with DC motor as input sources. Okay, the SEPI converter to operate PV at maximum power point. So this that SEPI converter is used to for the maximum power tracking SEPI converter. So this is the bidirectional buck boost converter to integrate battery and provides bidirectional power flow. Power flow means buck and boost. Okay, charging and discharging, that bidirectional power flow is happen. So after rectification of the PMSG output means after PMSG there is a rectifier is there. So after rectification, a buck converter is used for DC voltage regulation. It convert AC to DC along with step down the output voltage to require DC link voltage. So suppose now in the experimental setup, I have done for 110 volt DC bus voltage. So that suppose this output of the rectification, suppose 230 or 240 volt, and up step down to 110 volt. Okay. So this is the setup. You can see that this is a PV emulator. I have used PV emulator as a source. So it is a SEPIC converter is there. So SEPIC converter, after SEPIC converter, DC bus is there. So this is a wind emulator. You can see that wind emulator PMS, that PMSG is there, coupled DC motor. And this is the buck converter. After this buck converter, that the output of the buck converter goes to the DC bus, and you can see this is a bidirectional buck boost converter is there, and this is the battery bank. Okay, so five. Now I have used a four battery also that are connected in series. So this is a bidirectional buck boost is there. So charging for discharging. This is the R load, means only the R load. This is a programmable DC load. So by using the programmable DC load, we had fixed power, constant current, constant voltage, anything. So this is the experimental setup block diagram for the PV wind battery based DC microgrid system. So this is a SEPIC converter design. So we have done the design specification design. We have done the design in our lab, all the converter. You can see this is the SEPIC converter. Okay, so this is the inductor L1 also there. Okay, you can see L1. This is the L1. This is the L2. L2 value is 6.05 millihenry, and CL1 is the 6.08 millihenry. That core we have used for the making inductor, that E8040, that I have already told that in the morning session, that in designing part, that we have designed the inductor also in our workshop and also in lab. So this we have used the E8040 core for the for making the inductor. So copper wire for the inductor is W12 SWG. So depends on our current rating. You have to use, suppose to 16 SWG, suppose 18 SWG, like that. So our I want that current rating more like 20-25 ampere. That's why I have used 12 SWG. Okay. So this is capacitor one for after PV motor. You can see that what is C1? C1. This is the C1. This is a 4700 microfarad capacitor I have used for the stable the for DC voltage, also minimize the voltage ripple. Okay. So I can see the capacitor C2, also capacitor C3 is there. Their value are same, 2200 microfarad and 450 volt DC. And switch is there. The semicron, the IGBT module switch is there. So these are switching protection circuit also there. Switching protection and driver circuit also there. So there's a bladder resistance there in capacitor. You can see that bladder resistance there in the capacitor, top of the capacitor, for the discharging the capacitor voltage. Okay. So I have given the I maximum is 8 ampere, and V max is 250 volt. For the 1 kilowatt, we have designed for the SEPIC converter. So and now go for the buck converter design. After the PMSG output rectification, that goes to the buck converter. So you can see that there the inductor value is 1.92. This is the inductor. One inductor is there. So there 1.92 millihenry. The core is same 8040, and copper wire are same 12 SWG. There's a capacitor, but C2 value is low. It's 1200 microfarad and 440 DC volt. And switch is semicron. Switch is semicron, same IGBT module. This is switch, semicron IGBT module, and bladder resistance. So we have designed for the buck converter like for 2.5 kilowatts. It is because that heat sink is little bit big. That's why the current rating is so high. 10 ampere, it can handle 20 ampere also. Bmax 250 volt. So Bmax is 2.5 to, I think, for 4 kilowatt. I think 4 kilowatt it will can handle. A switching frequency 15 kilowatts. So this is the bidirectional buck boost converter. I have already told in morning session that bidirectional buck boost converter, that inductor is 2.3 millihenry, and core is 8040, same. And copper wire for inductor 12 SWG, capacitor 2200 microfarad and 450 volt DC. And switch is like a semicron IGBT module, you can see, and switch protection. So this is a bladder resistance also there. So you can see that this is a bladder resistance. A 5 watt The rating is 5 watt and 22 kilo ohm. And driver circuit is there. You can see the driver circuit and snubber capacitor. The snubber capacitor we have used for the switch protection to for 0.22 microfarad and 1000 volt DC. For the switch protection also, we have used also circulating current, minimize the circulating current. We have used the snubber capacitor. So this can handle Imax is to 50 ampere, Vmax is 250 volt. So these are power rating 2.5 kilowatt and frequency is 15 kilowatts. So it can handle 2.5 kilowatt to 3 kilowatt. So this is the designing part. So next Next, you can see this is the PV emulator we have used. I have used. So this is a PV emulator. That PV rating you can check that P is the 2 kilowatt for the 2 kilowatt solar system and voltage is 100 voltage and current in 20 ampere. So and SEPIC. This output of the PV emulator goes to the SEPIC. This that lead acid battery we have used for the in microgrid. That battery capacity to 42 ampere hour and 12 volt. This is the microcontroller we have used for the controlling the microgrid. So there is a pin is there. You can see that most of the pin is there. You can see that 1, 2, 1, 2, 8, 1, 2, 1, 2, 3, 4, 5, 6, 7, 9, 10. So this is the TMS 320F2 28379D board. So CPU 2, the clock frequency 200 megahertz. So that is a PWM output for the buck converter. We have used the 38 number pin. Okay, 38 number pin. You can see the 38 number we have used for the buck converter output. So for the PWM output. For the BTC, we have used for 40 number pins, and for the SEPIC converter, we have used 80 number of pins. 80 number pins means that you can see that 80 number pins is there is 80 pins. Okay, 80 and pins and ground is there. Okay, and a 440 40 number pin is there. You can see 40 and 39 38. This is the PWM output. Okay, this is the analog input also for on. This is a conclusion that the experimental result confirm the proposed control strategy enhance the grid stability, improve the power quality, supports seamless energy system, integration at small scale levels. So hence 500 TC microgrids are the practical prototype, future scalable, smart. So now I will play the video. Okay, I will play the video. After that, I'll go for that harder portion. Harder portion I will play, but if you have any confusion after that, you can ask me. Then I will go in harder section. So there is a, I think no sound is there. No, I think sound, any sound is coming in video. No, no. Hello, hello. Am I audible? Hello.
Yeah, you are audible, but no sound is coming.
Yes, sir, audible.
That sound is not coming. Na, for that video sound is coming.
No.
No, no, no.
No, na? So I will tell. Okay. So you can see that is the PV emulator. Okay, this 2 kilowatt PV emulator. Okay, so we have to connect to the laptop to the running the PV emulator. So you can see that I gave 60 volt and near about 2 ampere current. Okay, that output of the, you can see there is a 60 volt. Okay, 60 volt. Okay, 60 volt and current. And then after the switch on the SEPIC converter, also PV panel, PV emulator, you can see that current goes to near about 2 ampere. So you can see. So you can see that this is the 6000 microcontroller. So that I have used 80 number pin. So for the CP converter, that I have given duty ratio near about 65%. Okay, so that 60 voltage going that 60 voltage, that input is the 60 voltage, output is the 110 voltage. So 110 voltage is the DC bus voltage constant. I keep constant, so you can see that after running the SEPIC converter, okay, that I'll give, okay, then turn on the PV emulator. You can see that after turn on the PV emulator, that current near about 1.6 ampere. You can see it goes to 1.6 ampere. So after that, so you can see that the output voltage, output voltage near about, you can see, but output, you can see output voltage is 110 volt. Okay, so this is the SEPIC part is completed. Now I'm going further for the battery section. You can see there's a 4 battery has been connected. Okay, has been connected in series. Okay, so 4 battery is 48 voltage total series. 48 volt. So this is a bidirectional buck boost converter. You can see the bidirectional buck boost converter. So now it's like as a boost converter, because now battery is discharging through load. So load has been connected. So now I switch on the battery. That battery. Okay, battery means not a buck boost. Buck boost. Turn on the buck boost. Then you can see that the output voltage of the uh, buck boost converter, bidirectional buck boost converter, uh, you can see that is near about 111 volt, near about 110 volt, because you have to constant all the voltage. You have to output voltage has to be constant, because if voltage is little bit like some 90, it will come, that is circulating current will flow, that will damage your uh, so this is the auto transformer, single phase auto transformer for the wind emulator. For the PM is DC motor is there. So there is a armature supply and for the field supply. So 3-phase auto transformer we have used for the armature supply and the field supply for the single phase auto transformer I have used. So you can see that the output of the PMSG going for the there, you can see there's a rectifier is there. Okay, the rectifier, the 3-phase rectifier converted to DC output. The DC output goes to the buck input. The buck output goes to the load. So load is you can see that the what that output also has to be that output voltage has to be 110 volt. You can see that now it's coming 81 voltage. So we have to increase the armature voltage. So now increase the armature voltage, and then after PMSG output it got 110 volt after buck output. Okay, so now 3 voltage means 3 parallel means output of the SEPIC, output of the buck converter, or output of the bidirectional buck boost converter 110 volt. Now I have integrate, so I will integrate all the things. You can see that is the DPDT switch is there. So for the integration purpose, we have used the DPDT switch. Okay, so you can see that is the for battery is the wind. Now, you can see now I have integrate all the things, that integrate all the SEPIC, then SEPIC, after SEPIC this is the battery section, and this is the wind section. The 3 part I have indicated. This is a DC power load section also. Okay, this is a DC power load. You can see this is a DC programmable load. Okay, so all the MCB now turn off. Okay, because that load has been turn off. Now all the load is the DC programmable load. Okay, so you can see this is a DC programmable load that can manage the power also, or constant power, constant voltage, constant current. You can see that now current voltage is 110 volt and current is 2 ampere. Okay, you can see 220 watt in DC programmable load. Okay, then SEPIC, this is the for the battery. MCB is there. This is the for wind. Okay, now this can, then you can see that 110 volt is coming, 2 ampere means 220 watt. This is a DC power, DC volt, DC bus voltage, DC bus current, and DC bus power. now we are going up to 500 watt. So you can see. So this is a constant current mode. The current is increasing 3 ampere. You can see that 330 watt. It's coming. 330 is coming. Then go about suppose 5 ampere. Now we go further for 5 ampere. You can see so for 4.5 ampere. So you can see the near about 450 watt will come. Okay, 450 watt. So now increase the SEPIC input. Suppose it wants the SEPIC input. So now you go for 4 ampere current. You can see that 4 ampere current. Now 3.2 ampere after. So this is a 109 volt, 109.6 volt, and 4.5 ampere. So near about 490 watt. So about 500 watt I got. So like that you can go further. Means 1 kilowatt, 1.5 kilowatt, 2 kilowatt, like that. So we have tested for also 2 kilowatt also. So there's a now turn on the MCB. Turn on all the MCB part. Okay. Now current. I decrease the current rating. You can see there is the decrease rating. Now turn on the MCB. Now that programmable load has to be off. Then all the DPG switch has been opened. So now all the sources are disconnected, and this is the win. So thank you for this part. So so this is the conclusion. The experimental result confirm that the proposed control strategy enhance grid stability, improves power quality, and supports seamless renewable energy integration at small scale levels. Hence, the 500 watt DC microgrid serve as a practical prototype for future scalable smart microgrid application in residential and commercial remote power system. So this is a reference. Thank you. If you want to show again the other section, other means camera, okay, then we'll do also. So any question further? So any question about the experimental setup?
Is there any queries? Please let us know.
Sir, you
If
are
you
using
want-
that what you call DPST switches, right?
Yes.
The purpose of the DPST switches is you want to say that you are integrating them, right?
Yes.
That means solar and wind you are integrating, and battery also you are integrating. That integration
Yes.
is represented by DPST, right?
Yes. This is the DC bus. After that
Okay.
integration part.
Okay, the DPST is nothing but DC bus bar.
DC bus. This is a DC bus. After integrating all the part, this is called DC bus.
Okay. Load, what is the load, sir? You have used DC loads, no? I mean, a resistive load you have used?
Only resistive load. Only resistive load. Only resistive load I use only. You can see that this is the DC programmable load. This is a DC programmable load. You can see this is a DC programmable load. Okay. You can do for constant current, constant voltage, constant power mode. You can change.
Okay, advantage with the DC power load is programming load is you can either operate in constant current or constant voltage.
Constant voltage or constant power also.
Okay. Thank you. Okay.
Sir, hello.
Hello.
Sir, one question. Sir, at the input side of diode bridge rectifier, have you used any capacitor bank? Otherwise, your PMSG will not be sine wave.
This is a battery management system. This is not I have
No, no.
done battery management system.
No, diode bridge rectifier. After PMSG, you have used
Yes,
a
yes, yes,
three-phase diode bridge rectifier.
Yes.
It's a so you have to use a capacitor bank. Otherwise, it will not be sine wave, right?
No,
Actually,
because I have
PMSG output, then it is rectified. Okay. So rectified to DC. There is a one converter. Okay. So
yes.
yeah, as we
But
are
the
rectifying, yes, sir. That's why we have not
but the
used yes.
but the input side it will not be sine wave.
Yes,
Yeah.
that definitely.
Okay, sir.
if you want camera section also, if you any participant want, so you can go
Is
for
there any
the
other
camera.
query? Is there any other queries?
Sir, regarding the switching of the devices, you are doing that by using the microcontroller that TMI, that Texas Instruments, that F28339, right?
Yes.
Okay. Yeah, I mean, we can implement the in the place of that DSP board, you can use either FPGA or DSpace or anything, right?
DSpace is a very costly. That there is only
Okay.
4,000 to 5,000
Anything
rupees.
can be used. Yes, that can also be
Anything can be used.
Riju,
But
just
that
listen. Hello, Riju.
Sir, please.
yeah.
Please listen the question carefully. Then you respond. He's asking about instead of TI's launchpad, you can use any other platform or not. So answer is that yes, it can be used DSpace, it can be used Opalati. Both can be used, sir.
No problem, sir. Thank you.
Any other question from the participants end? Hello, is there any other queries? Okay, so I think there is no other queries from the participants end. So we can conclude the session. Okay, we can conclude the session. And okay, I think this is very good interactive session today itself. Okay, so tomorrow morning again we are having the session that will be started from 9 a.m. sharp. Okay, thank you. Again, we will meet you on tomorrow morning. Okay.
Sir,
Bye.
thank you, sir. Thank you.
Good, sir. Thank you.